calculate this, or should we continue with contracted too?
Before the start, chapter 2, my question is this issue.
Yeah.
We consider this steps, but we do not consider this steps because this cannot.
No, I made a measurement. I have had a problem, and I made a measurement with a field strength, magnetic field strength. It was copper, like this,
Yes.
50 hertz. I made a measurement with a Hall element, and I measured the field strength. The field strength, if you have such a copper bar, the field strength is all the same, always between here, and it decreases here. So it means the current density, if you have such an arrangement, you don't have current displacement in this direction, only in one direction. I think this is what we have to calculate.
Yeah.
This is if you have we only have current density, we only have to calculate this. This is not important. So we have current displacement in x and epsilon direction. That was your question. And the current displacement is either in one or in the other direction or in both directions. If you have this,
Yes.
I think it's full copper.
Yes.
I think you have to do this here.
Yes.
But if one direction is small and the other is not, you have current displacement in one direction.
One direction.
Only in this direction. I have already have to learn in the last 15 years too. If I was ready with the study, I thought we have the same, that we have current displacement in this direction. No, we have if this if this direction is small and this is long, you have current direction. It's a practical experience. You can't directly not see it out of the differential equation, but in practice it is so, and we already examine it by measurement.
The current is flowing at the surface of some millimeters on the surface.
Yes.
And if you have a steel arm and put copper on it, it's flowing only in the copper. Maximum is 8 millimeters. 9 millimeters. 9 millimeter at 50 circles per second. At 60 is the circles per second. The current density, in the deep is a little bit smaller.
9 millimeters.
9 millimeters. A little bit smaller. It's only flowing on the surface, therefore it's not flowing in the steel. Ja. Wir haben mal in dieser Publikation, the publication, können sich noch erinnern, in unserer ersten Publikation, da haben wir das mal ausgerechnet.
Ja.
Wo man, ob ich sie finde.
die Kappa-Arm들이 스틸이야. 스틸에
Here.
카파를 이렇게 붙인다. 그렇기 때문에 이 붙이는 사유가 그렇게 내고 스틸이잖아.
네.
결국은 이 바깥으로만 전류가 흐르기 때문에 이런 형태로 쓰는 것 같아, 사유가.
Können Sie sich daran erinnern? Ja.
그러니까 9mm, 10mm 그 사이.
Die habe ich gesucht, die ganze Verabredung.
Ja.
Habe ich nicht wiedergefunden. Die liegen irgendwo, also
Ja, können Sie erklären, was das ist? This is our common publication about the first current conducting electrode arms. And
asthma in
48.
84.
Yes.
84.
Yeah.
And we calculate that the resistance with this method. And if we have A and B, and that is 4 millimeters.
Yeah,
We don't have carbon. And if we have B and C, we have 20 millimeter,
Yeah.
and we have current, we have suppression. No? And here also. And here's copper and iron, and the iron is, or the steel is not important for the reactant because the
This
current.
publication is on your CD. Yeah. And this was our first, our first lectures about it is possible to make copper-plated current conducting electrode arms. There's no current, very few current flowing in the steel.
I think we thought about this about 83, and this publication is from 85.
Yeah. And these were the first. In asthma steel, you see here the different electrode parts. These were from water-cooled copper, and these were graphite. But this did not work because the handling is very terrible. Handling, yeah, and therefore they use spray cooled graphite electrodes. Yeah, okay. Okay, this is in your CD, the publication. This is the first publication about copper current conducted electrode arms. Okay? Good? And there's more. There's more. Yeah, this is the current in the surface. This is the copper part, and this is the steel part. You see, most of the current is flowing, and a very few current is flowing in the steel part. Yeah?
I did not know that I have calculated this, but I calculated this a long time ago.
그러면 진짜 이거 같은 경우는 그냥 이쪽에만 카파가 붙어있는 거잖아요. 그래서
그렇지.
그쪽만.
Okay, I do not know how thick this was, but it is, yes,
Yes, 6 millimeters.
6 millimeters.
But you see that most of the current is the integral of the current density. This area is very big and this is very small. It means all the current will be almost the current will be.
Is it your question? It's a very important question because you have to decide if you make copper conducting, current conducting arms, how thick the copper is.
Yeah.
Yeah, but this costs money.
Yes.
There are different constructions. We have current conducting arms with the kappa, which is by explosion put to the surface,
Yeah, yes.
and by roll mills. Yeah, I do not know what kind you use.
I don't know in our structures how can make this kappa.
Yeah, this kappa to the surface.
Yeah.
There are two ways. The one way is with a roll mill,
Yeah.
which is work together,
Yeah.
and the other is by explosion.
Yeah. Explosions. Contact
Yeah,
history.
boom.
Yeah.
And you can only make this in a country where not many people are living. It's made in Europe, in Sweden.
Yeah.
They go into the forest
Yeah.
where not many people are living around, and they make boom.
Yeah.
Both solutions are possible. Okay, very interesting question. Very much know-how in it, in this paper, yeah?
Did you take a picture? This one?
Yeah.
Then this one, please.
Yeah, you have this on your CD. Yeah?
CD?
Yeah. Look into the CD.
Okay.
Try now. We have enough time. We have 1 week time.
Yeah.
Ja?
Das ist das Ele 85. Ja?
Ja, ja.
Das sind also Files on the CD.
Is Windows 7?
Yeah.
Yes, 7.
I have now a computer with Windows 8.
Yeah.
It's not necessary.
This is not in color,
Yeah.
but it's on CD.
No, it is not. Publication, Ele. 2 Ele. Number 7.
Number 7.
Yeah. Click, make a double click. Yeah, he's loading. He's loading. It's coming there. No, this is not correct. Yeah, this is. You see that? Next.
question.
Yeah.
You see that?
Yeah.
Okay.
Okay.
This videos.
You see that?
Yeah.
Okay. This is
What is the
we
good
have success.
situation for Israel leaders are skin depth? Is skin depth?
No, it's less current suppression. It's less. It's only 4 millimeters. 4 millimeters. If you have 4 millimeters,
Yeah.
you have no current suppression. And you can see it here. The current density in the copper is almost the same at every time. At every place in the copper is the same.
Okay?
Then,
This is okay, yes?
then you don't have current suppression, displacement, current displacement.
Okay, nehme ich wieder mit. Okay. If you have questions like this, please hold your hand and say, I have a question. Yeah?
If you have questions to this, you have to. Always have to ask. This is the last example of chapter 1. You have to decide. We have time enough. If you want for better understanding, we want to calculate, or we want to continue with chapter 2. That's your decision. Shall we continue? With 2? With 2. Phosphor lesson, chapter 3.
Wir haben schon in der Hand gehabt, Kapitel 2.
I have a printout of chapter 2. That's my printout. I put it in my printout. So.
These are all the publications that are fundamental, most in German language, some in English language. Yeah. Well, you see, we both have worked together since more than 20 years. Yeah.
30 years.
30 years.
30 years.
Yeah, no. Yeah.
83. It's.
He's 59 and I'm 74. You see, and we have worked for several years on this problem. Yes.
So I have to see where we are. And push it. Yeah. Phosphor. Phosphor lesson, it means chapter 2. So, chapter 1 was normal theory of electrical engineering. Chapter 2 is the theory of reactance calculation for conductor reinforced reactance. We have two parts in this chapter, some red and some black, and the black is theory, the red one is all again the common what we have to do. So, how to calculate inductance or reactance? We have as a formula that in a magnetic field the electrical energy is 0.5 inductance times square of current. That means if you know the current and the energy of the field, you know you can calculate the inductance. But how to calculate the energy in the field? You have to integrate about the volume. And then you can you have here the current, and you have here the electric field strength, and you have to integrate about the volume. That's very complicated. So you can solve this formula to L, and you have to integrate the volume and divide it by the square of current. And you don't have only one conductor, you have more conductors. And for two conductors, it is shown here. Each conductor has a current, and this current in each point of the volume makes electrical field strength. And how to calculate the field strengths together? You have to calculate a vector addition. Superposition is it. You have one current, the other current causes and you have to add as a vector addition. And so you can, about the sets of cosinus, with the cosinus, with the help of the cosinus, you can calculate this, and then you will get 4 terms. And what are if you calculate this, you will get 4 additional terms, and one term has only caused by current 1, caused by current 2, caused by current 1 and 2. So we can say we have energy 1 if you do the afterwards this integration, we have 4 parts of energy. Energy of conductor 1, energy of conductor 2, and coupled energy. And if you use this for the 4 parts, we will get the same as in the last chapter. In the last chapter we got self-inductance and also self-inductance of conductor 1, self-inductance of conductor 2, and mutual inductance. And this in the energy, this part which has coupled with current 1 and current 2, that is called mutual inductance, or mutual reactance if we multiply it with the angular frequency, or 2pf. So we have now to calculate 4. If we have 2 conductors, we have to calculate 4 inductance, whereby the coupled inductance is always the same, because you have here 2 times the half, then you get the same expression here, and this is and you can see this is caused by for mutual inductance. That is important for only the red one you have to understand, and the other is only nice to know and necessary to know. So, if you put in now you have to put this h in the integral. Where you get it from? I don't tell you it in this paper, and I don't tell you it in the book, but I don't know self how to get. This is an expression. This comes from the Biot-Savart law. With Biot-Savart, you can calculate the magnetic field of a conductor. And you have to put in all the magnetic field, H1, H2. Now we calculate mutual inductance for axis conductors. That's easier. What is an axis conductor? An axis conductor is only if the current is flowing in one line with no cross section. For mutual inductance, it's good enough. For mutual inductance, it's good enough to calculate this in an axis conductor. In most time, not for all time. So, and if you put in all this is an integral, 1, 2, 3, 5 integrals. That's too much for us. And so you have, without derivation, we get the mutual inductance about this. This formula is the important formula for reactance or inductance calculation. This is double red. And we have to discuss the Neumannsche Doppelintegral. We still have a double integral. And this we have to discuss. What does this double integral say? So, I will tell you on paper. What do you have to do? I will call this. I have a nice paper. A, B, C, D, E, F. Okay. What have we to do? We have to calculate the mutual inductance between this and this.
Okay.
We call this 1 and 2. We have X is what?
Die Buchstaben sind da anders als bei Ihnen.
Yes, we have. Mr. Tim says, I always do the difference between the projection and Mr. Tim says we have other letters. So A, E, and B, C, F, and E. So, in this, before, we have to discuss L1 and that's a vector product. That's a scalar product of a vector. What does it mean? What does it mean if I have vector L1 and vector L2? What does it say? We have a angle, and it means now, let's know.
Yes.
So, what means it? And in this case, and almost in the ARF calculation, we have conductors which are parallel or which are perpendicular. And if we have parallel conductors, parallel L1 times L2 is that's right. If they are perpendicular, what do we have? What makes it? It's 90 degrees. Zero. Zero. That means all parts which are zero, which are perpendicular, do not have any reactance. I have had it in chapter 1. We have discussed this one. This one. That means I have had this one, and we have discussed this one. I did not paint this one because they're zero. That we don't have to calculate this one, and therefore, it's easy to calculate the reactance of the areas, and the sum of this is almost the same, because the coupling between here and here is zero. The coupling between here and here is zero, but this is complete calculated, and the transformer line, you have a coupling between here and here, but the distance is big, and if the distance is big, there's a less coupling. But we came back to this one. We came back to this one. What we have to do if we calculate 6 and 2, we have to calculate all. We have to calculate XA C, XA F, X A D on the same with X E C X X E F X E D and the first thing, so the next one, and this X D X D X D X B B 2 C F D. Have we indeed all to calculate this, or can we? This is something to do in this time, which is too much work. What is too much work if we do this? We have had here something. We look through here. Yeah. And here. And here. And here. And here. That are our vectors. We have to do the double integral with this scalar product. And what is X A E? No, X A F. What's that? Huh? Zero. More of them are zero. Yeah. Which are CO2 here. Yeah, many of them.
많잖아. AF, D, ED, AF, ED, CF, BF, 0, CF.
Yeah. So,
Yeah. So this is plus AD minus.
okay. That's zero. That we don't have to calculate. If the post-reactance calculation program calculates it, but it calculates all. It's too stupid. It says I have a conductor here and a conductor here, and if it calculates, it comes zero out of it. Yeah?
Yes.
And if you have a zero in a sum, it's not proper. It's not important. No? So that's very important. So
Yeah, also the flexible cables.
Yes.
Yeah, there's an equation for this, but we say it's the same length.
Okay.
This is for making an easier calculation, because there's no mutual inductance between these vertical and horizontal parts. Yeah, this is what we know, and also this is a special equation for this, but in most cases this looks so.
Yes.
Yeah,
Yeah.
because this is like a half circle in most cases, because of the flexibility of the cables. This is the difference between this and this is small. We neglect that. Okay.
Yes.
okay, what's about this sign? Self-inductance always positive. What's about mutual inductance? Mutual inductance is positive or negative?
Yes.
Can it be negative or positive? So we go to the vector calculation again. If we have this one and this one, then what I have to put here? Minus. Okay. If we calculate mutual inductance is either positive or negative. And now we have to look here what is positive and what is negative. The zeros, zero, I will read it.
This is not
That's
minus.
That's zero. So, and we put the sign here too. What's the sign AC? Plus. What's the sign AD?
Minus.
80
Minus. Why is ID minus? You can see you have to look. So you have to look for the current. If the current is flowing in this direction, you have opposite direction. Opposite direction gives minus reactance. Mutual. Mutual reactance. So, exercise complete. EF plus. Then we have BC minus plus. So,
And in this paper, the mutual inductance between this minus or plus? Minus, and between this, zero. Also zero. Okay.
So, we will make an exercise, x1, 2. We begin with x, a, c. So, then minus x, a, d. That's if xad is positive. If the program calculates it as negative, but if you make it manual and calculate xad, then you have to say this one. That you have sure that xad is positive. So next time AF is 0, so we have to do nothing. And now B. Minus or plus X B C minus and plus I know that the last one is positive. X D is positive. And it's all.
This part?
Yeah. X, yeah. The same direction. So,
this part, we not consider this as here. Why?
it's not considered because if you consider long conductors, 5 meter long, and the distance is half meter, this one is very less. Therefore, it is not considered here. But Mr. Tim has already painted the flexible cables. And for the flexible cables, we have considered this because it's a part which is important for reactors. Okay, this is the introduction, and this is called the von Neumann'sche Doppel integral, and this tells us something about how to add reactants. You have, if you have to calculate the mutual inductance between two loops, you have to do the sum, the double sum. You have this, and sometimes it's 0, sometimes it's negative, sometimes it's positive. Okay, we'll see what the next is. Here is that shown, what you already asked for this. I did not know what the next step. I was in vacation, and before the vacation I prepared all the things. And yesterday I looked at this, but I did not know what is coming next. And here the reactance is the same as here, but it's forgotten EF. Already remarked here. So This is the same as here without this, but it's better I tell it on paper as all things I presentation. And in university I will pick Tafel. What has Tafel?
Table.
On the table was Kreide. Kreide.
Okay.
With a white thing you can Leo. I put in EAF, and EAF in English he said abbreviation for electrical arc furnace. I will put a German word Kreide in. I have switched off.
Your phone.
Mine?
Yeah.
Oh. Oh. Weggedrückt. Gucken, was ich tue. Soll ich da zurückrufen oder später? Later. So. Das Einloggen. It's not so important for AIF calculation. I think I will prepare later. So that we tried in the exercise already.
Sind die beiden Ströme eigentlich gleich? Denn in den beiden Schleifen gewesen, I1 und I2?
Das ist uninteressant. Es ist ja nur eine Reaktanzkalkulation. So, the next example. The next example, I will show you. Das ist noch. So.
Sind das zwei Seile, zwei Ofenseile, ja? Zum Beispiel.
That is a theoretical example. It has nothing to do with EAF, but it's an exercise. A, C, D, and B. And here we have E, G, H, and F. So, I will show you how to calculate. We begin with A, X, X, 1, 2, X, A, positive or negative?
Positive.
I think for help we can do this. Mr. Eam did it already by the last example. The current. So this one. So I think we can decide. We will start with A. A to G, 0. A to H, plus or minus?
Minus. H.
A, H. A, F, C. Okay. Plus C, G, plus or minus?
C는 F.
C, F,
Yeah.
C는
minus, huh?
마이너스
minus.
S, D.
D.
Gehen Sie ruhig an.
G.
Alles? Hallo Frau Oltmann, ich gebe mal meine Frau. Ich bin in Hamburg und halte ein Seminar und meine Frau ist im Nebenzimmer. Frau Oltmann, ich hoffe, Sie sind wieder gesund. That's our neighbor. The wife is 80 and is in hospital.
Ja?
So, X, D, C,
D.
D, H, D, E, minus,
Yeah.
and we have D, we have X, X,
B. C minus
the F is
F and
positive, and G is minus.
Yes.
So,
Yeah.
that's all.
Yes.
That's important to know. So, let's don't look to this one. And I think this exercise you should do on paper.
Yeah.
Don't look to the
Okay.
don't look to the solution.
Okay.
Was sagt man?
Braucht die jemanden, sollte man, die kriegt einen Rollstuhl und ich sollte die Garage aufmachen. Jetzt muss ich sehen, wen sie in die Spur schickt. Ich bin aber nicht da. Entschuldigung für die Störung.
Nein, Sie müssen jetzt recht. Tim ist entschwunden.
Was dann? Hier, hier, hier.
So, I think that was the first step, that we have to make the von Neumannsche Doppelintegral over all conductors and how to calculate now this part reactance. That's the next step. First we have to make something with the reactance. Each part, if we in a arc furnace, it may be that then the flexible cable, very taut arm, and so on.
Yes.
So as I have 1, 2, 3, 4, 5, we make this one.
Yes.
No, and then have here you have 3 or 5 things we have make the exercise with, and now we have to say how. And now we are at the mutual reactance. Mutual reactance. That means this is the phase A. We have to do the phase B. Later we will have the self-reactance. Say how to do the self-reactance. And now we have one line conductors. One line for each conductor. We have to make the next step. For many next steps, but we have to go step by step. Okay, I think you have understood, and that's good. So, Mr. Tim already told what to do with a flexible cable or with other things. In all things, the conductor has a self-reactance, and for this self-reactance, it's important that the length is not changed. That's important. The biggest size for reactance calculation is the self-reactance, and the mutual. But now we discuss about mutual reactance. We will see that the self-reactance is calculated in the same way with the geometric mean radius, which we introduce then. And so we have to make... Lichter? Oh. Alles? Ach so, ja, nee, das war, ich hätte was Falsches gedrückt, ich hätte das in der Tasche und ich erzähle gerade hier in einem Seminar was, dann noch gute Besserung und vielleicht sehen wir uns ja bald mal. Wir sind Donnerstag wieder da. Okay. Sorry? That was our neighbor. I have if you call me at home, it will become to here. Okay. The important thing is that the length of the part D is the same as the length of part E, F, and G. Same length. So we have to arrange this. Also flexible cable. We have a chapter 7.3 or 7.4 where I have explained it also. But important is that the same length is so. And now we have here a result for parallel conductors. For parallel conductors, the von Neumannsche integral with the limits, we have 4 limits, and this all 4 limits have to be input in this equation. So I will go to the projection. So that's a double integral. You have to put 2 limits for each integration. So you get here for this arrangement with this length and this conductors which are parallel. if we have excess conductors, we have line conductors. We have here a distance, the parallel distance between this. We call it G12. Why? Later we will call this geometric mean radius. But in a moment for no?
No. Question?
No.
No.
I heard. I don't know where Professor Tim is. If you solve this integral, it's to calculate. It's not. You have to do some substitution and you have to put in the limits. You will get 4 limits. 4 limits. Plus, minus, plus. So that's the exact formula for this configuration. And this is the most used formula for the post-covariance calculation program. That for parallel conductors, the program calculates all these values which are here out of the. You put in your coordinates and the program calculates all these values, and you have to use this formula. What is easier? What is easier? You have a sub-program which calls this, and you see here always the same. Here is L2 minus L1 and so on. Here is L2 minus Z. It's always the same here in each. This 4 times different, and therefore you have a sub-program where you call this and put in these V values, and you can calculate this formula by this formula by this formula. And this is one which is used for the program. So, and then here's some 2 special cases that the conductors. It's not. No. The room is cleaning here, and therefore. But we have to not to stay Mr. Tim outside of the room. So, this is one what you can put in. Yes, so you have to try it, and then you have the reactance of a part conductor which are parallel, and you can use this formula. If you have 2 parallel electrode arms, the begin and end are always in the same plane. If it is this, it's easier here. It's very easier. And most of the examples I showed to you are with this formula. Only the additional reactor in the exercise has to use this formula because it's not parallel with the same angle. So, and if the conductor is very long, against to the distance, then you get this formula, easier formula as this. Mr. Tim and I, when you the first furnace we calculate was this furnace in the publication you have seen. There we used first this formula. That was our first furnace we calculate. And then we used this, and afterwards this formula. It's a development since 1883. So,
G1 or G21 is GMR? Do you mean GMR?
that's GMR.
GMR.
But now we don't know what is GMR, therefore it's called G. That's later it's GMR.
Yeah.
That's now we have access conductor. That the current is flowing in the line.
In this case, if this error is how long?
If afterwards we have examples, and we can compare the left formula with the right formula. And if you use the left formula, it's not wrong. It's not wrong to use the upper formula. It's a step. It's easy, complicated, most complicated. And if we make it manual, and first we have done all this, we have calculation with the program. We have this first copper-plated furnace. We have calculated manually. Then Mr. Ehle, I don't know if you know Mr. Ehle.
Yeah.
It's,
How much ton was how much ton? Tons capacity?
Mr. Tim is an expert of ERF and knows all the data. You have to. It's a relative big furnace already. I think. Oh. Mr. Tim, Mr. Jin just asked how many tons asthma steel furnace. I don't know.
I will have a look. This is my book of arc furnace publications.
Yeah.
I put this together when I retired. There's $365 days trouble-free operation. Okay, this is not shown on that. We will have furnace asthma. Yeah, it's not very great. I think this is 60 tons. I think so. Yeah. This was the first photo of this system. Yeah, but it is old. The paper is from 85. Yeah. Yeah. 36 MVA. 40 ton. Yeah, a small one. Like a ladle furnace. The question is answered. This is my job.
So, I think now we can calculate the mutual reactance between two parallel conductors and have an axis, only where the current is flowing in one line. The next one is that we make this area bigger, this line to an area. Then you have to substitute the current by the integral of the current density. This causes that the current density all over the cross section is the same. Otherwise you can't do this. Otherwise you have to solve the proximity effect and the skin effect, or by methods of the electrical field. But if you say the current density is always the same, and you have seen that if we make this with the skin depth and we calculate the resistance, it's always the same, the resistance and the conductance. That the error is not so big that we can do this. We make out of a line, we make an area, and then we have a most complicated expression with 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 So, that's most complicated. Have we do this integral? No, we don't have to do this. We have already this formula. This formula, this gave the result from the last. This one. This gave this one. This one we can do. It's not complicated. Not so complicated. But we have now to substitute. Now have we to substitute this. In this formula we have G1 to 2. And now we have to substitute this by this formula. What is this? What is this? And this is called in calculation GMR, geometric mean radius. So, what is it? That means if we have not line conductors, we have to use the geometric mean radius. What is the geometric mean radius? It's easy to calculate. No, it's not so easy.